Hello, my name is Prasad Subramanian. I am a professor of physics at the Indian Institute of Science, Education and Research in Pune, and I do astrophysics with an emphasis on high energy astrophysical phenomena, on plasma astrophysics with applications to phenomena like the solar corona, accretion around black holes and things like this. So this is my broad area of research. In much of what I do, I need to consider the dynamics of fluids in astrophysical situations. Odd as it might seem, normally we think of astrophysics as having to do with planets and galaxies and black holes and discrete objects like this. But nonetheless, in fact, fluids, the kinds of fluids that we encounter in everyday life, air, water, gases and things like this, the dynamics of such fluids are of central importance in understanding astrophysical phenomena. The fluids might not be the same, the character of the fluids might not be the same, but they're fluids nonetheless. So I figured I would give this course on the dynamics of fluids. This course provides a broad overview of fluid phenomena in astrophysics, and the first few weeks will cover the basics of fluid dynamics, the kinds of which you will find in pretty much any fluid dynamics course, be it taught by someone doing lab fluid dynamics or engineering or so on and so forth. The basics are common to everything. There will be a little bit of tailoring towards astrophysics, but not that much. So we will essentially cover conservation laws and things like this. So this is what we will be doing in the first few weeks. The slight emphasis will be on compressible phenomena. This is because this is what the basic emphasis, this is what astrophysics mostly deals with, compressible fluids. So our coverage of the basics will be biased by that. These basic concepts, of course, will then be applied in roughly the second half of the course. These basic concepts will be applied to understanding astrophysical phenomena ranging from the solar wind to black hole accretion disks. And then we will talk a little bit about magnetic fields, because magnetic fields, although the bulk of the course will not consider magnetic fields, we'll simply talk about unmagnetized fluids. But magnetic fields, however, are ubiquitous in astrophysics, in all kinds of astrophysical situations. And so what really is important in astrophysics is the study of magnetized fluids. And this is a branch of fluids called magnetohydrodynamics. So we will spend a little bit of time understanding the basics of the basic framework of magnetohydrodynamics, and then we will apply it to understand astrophysical phenomena such as dynamos. This is one of the phenomena. This is one of the ways magnetic fields are generated in astrophysical situations, and jets from black hole systems, and so on and so forth. So broadly, this course will be talking about the basics of fluid dynamics, applications to astrophysical phenomena, a little bit about magnetic fields, and the basics of magnetohydrodynamics, and then go back to applications which use magnetohydrodynamics to understand astrophysical phenomena. So upon completing this course, students will be well equipped to understand a broad range of research literature in astrophysics, specifically having to do with astrophysical fluid dynamics. Hello, welcome again. So this is the point where we plunge right into the course. So this is the course on fluid dynamics for astrophysics. I am Prasad Subramanian. This is my email address, and I work at the Indian Institute of Science, Education and Research in Pune. So what this course is useful for is it's useful for students who wish to gain an overview of the vast field of fluid dynamics. Fluid dynamics is really a vast subject studied by many people, engineers, lab physicists, to all kinds of engineers for that matter. And we here will be by some biologists and it's really a very wide-ranging field. Here in this course, we'll be concentrating on applications to astrophysics. So the prerequisites for this course are really a basic understanding of classical mechanics. You need to be very well versed with conservation laws, such as momentum, mass, and energy conservation. A certain amount of familiarity with kinetic theory of gases would be good, and especially for the latter half of the course, when we will be talking about magnetic fields. Knowing about electrodynamics, especially about electromagnetic waves, that's essential. By way of mathematical preparation, I would expect a sound knowledge of basic vector calculus. In other words, you should be comfortable with things like gradient divergence curl and things like this, because we'll be using this extensively. Some familiarity with tensors is good, but not terribly essential. I will try to make this self-contained. Tensor calculus is useful but not totally crucial. Same with astrophysics. Although we are talking about applications of fluid dynamics to astrophysical phenomena, I really don't expect students of this course to be very familiar with astronomy. Some exposure is good, but if not, that's all right. We will be trying to introduce these things in a self-contained way. So coming to the organization of the course, we will be proceeding in the following manner. The first half of the course, probably more than the first half, will all be about basics, the basics of fluid dynamics. We will start with the continuum hypothesis. By that I mean the manner in which the study of continua, air, water, so on and so forth, is different from the study of point particles. Yeah, when you learn about Newton's laws, F equals ma, it's generally applied to a point particle, say a stone idealized to be a point particle. Whereas here we're not talking about point particles, we're talking about aggregates. Yeah, a gas, for instance, is an aggregate of several hundreds of thousands of molecules, and so how you apply these conservation laws that we're very familiar with to a continuum. So this is what constitutes the continuum hypothesis. And then we will talk about kinematics, which roughly speaking is about how a fluid responds to the forces that are acting upon it, without bothering too much about where the forces come from. Okay, we will elaborate this in a minute when we come to it, and all through we will be concerned with the basic conservation laws that are central to pretty much all of physics, the continuity equation, which is just another way of saying mass conservation. Mass is neither created nor destroyed. And then the momentum equation, which in different guises is called the Euler equation or the Navier-Stokes equations, right? So essentially we're talking mass conservation, momentum conservation. These are the two conservation laws we're talking about. So we will spend roughly 3 weeks on this, and after this we will go on to what are called dimensionless numbers, and this is one thing that's peculiar to fluid dynamics, plasma physics, and things like this. You don't work with dimensional quantities such as energy, momentum, and so on and so forth. You like to divide things with certain normalizing quantities so that you get dimensionless quantities, and there are certain dimensionless numbers which are very, very important and crucial to the study of fluids, and we will talk about that for a bit, and we will talk about what's called dynamic similarity, which is to say, for instance, let me give you an example. If you were to understand the dynamics of airflow over an airplane wing, right? So one way is to get a full-size airplane wing, place it in a full-size wind tunnel, and study the dynamics. So that's one way, and that should be done at some point, of course. But even before that, it's useful to look at the dynamics in a scaled-down version, right? A miniature airplane wing. Turns out that there are certain things to keep in mind. It's not like you can keep the miniature airfoil in the same fluid as the larger as a full-size airplane wing. If you want to truly capture the dynamics. So underlying this whole thing is a concept called dynamic similarity. So we will talk about that a little bit. It's useful for astrophysics as well, which is why we're talking about this. And so we will spend about 2 weeks on dimensionless numbers and dynamic similarity. We will then go on to talking about compressible flows because this is so important to astrophysics. Flows that are essentially squishy. Yeah, and the concept of the speed of sound, you're able to hear me because pressure waves from my mouth are hitting the recording device, and the recording device is converting them to electrical signals and then recording it, and then it finally reaches you. But this phenomenon of the speed of sound is something that can be understood only after understanding the dynamics of a compressible medium, because sound is all about compressions and rarefactions. So we will devote some attention to compressible flows, partly because the speed of sound and some other characteristic speeds are central to understanding astrophysical phenomena. And this is where we make a little bit of a departure from the way fluid dynamics is studied for several other branches. For instance, most engineering, at least a lot of engineering applications, don't concern themselves too much with compressibility. Incompressible flows are just fine for them. And so we will, in studying this, we will make some distinctions. Any given flow is neither fully compressible nor fully incompressible, but nonetheless these boundaries are useful, and so when we come to it, we will understand these things. So suffices to say that we will devote sufficient attention to compressible flows and to how the speed of sound is derived, and we will make a brief introduction to the phenomena of shocks, which are very central to astrophysics. We will spend about 2 weeks. Maybe this is a bit of an underestimate. Maybe we will spend about 2.5 weeks on this thing. So this is the next thing, and the second half of the course we will concentrate mostly on applications to astrophysics. We will first of all start talking about transonic flows. By transonic I mean flows that sonic refers to the speed of sound. So by transonic we refer to flows that transition from being subsonic to supersonic. In other words, flows that transition from being below the sound speed to above the sound speed, and there are some peculiar features that one has to be careful about, and the reason we will pay attention to transonic flows is, of course, because they are central to many phenomena in astrophysics, specifically these two kinds of phenomena, spherical accretion. Well, these are two examples that we will study. Accretion refers to the manner in which an object attracts matter from around it. It accretes matter. So it turns out that an isolated massive object such as a black hole or other compact objects, they often attract matter from around it in a quasi-spherical manner. And in order to understand the manner in which matter or the gas around it is accreted onto the central object, one needs to understand how transonic flows work. And another problem, as we will see, the math will work out that way, which is pretty much the mathematical formulation is almost exactly similar, except in this case the flow is not moving onto the central object, the flow is moving away, and that is a solar wind. Okay, some of you might know that the sun is constantly blowing out part of its outer atmosphere, which is the corona. It's constantly blowing out its corona out into space, and so this is called the solar wind. And in order to understand the dynamics of the solar wind, the phenomena of transonic flows is of central importance. So after having understood the basics of transonic flows, we will consider these two applications, and we will spend roughly a week on this. We will then, with a view to studying astrophysical jets, we will introduce a concept called the de Laval nozzle. The term de Laval nozzle originates in mechanical engineering, as it turns out. So just to demonstrate the close correspondence between different branches of fluid mechanics, we will first introduce the de Laval nozzle, and this concept was applied to understanding astrophysical jets. So this is what we will do for the next week, and we will then spend about a week talking about accretion disks. We already talked here about accretion, the manner in which matter from around a compact object is attracted towards a central object. Turns out that it's not always the case that matter is accreted in a quasi-spherical manner. It turns out that in certain circumstances where there's a companion to the central object, there's a companion from which the central object is attracting matter, there are certain circumstances in which the matter is accreted not in a spherical manner but in the manner of a disk. Okay, we will talk about the details when we come to it. So the accretion takes place in the form of a disk. So hence the word accretion disks. So we will spend about 1 week talking about accretion disks. Finally, we will as I indicated earlier, magnetic fields are central to much of astrophysics. They, in many situations, they control the dynamics fairly profoundly. For instance, the solar corona. Yeah. So far, we have not touched magnetic fields at all. We've mostly been talking about neutral fluids, and from now on, we will do a very quick job of including magnetic fields. It turns out that it needs to be included mostly in the momentum equation via what's called the Lorentz force. Certain modifications that need to be made in the overall mathematical framework, and these modifications are part of the field called magnetohydrodynamics, which, as the name implies, is hydrodynamics combined with magnetic fields. So we will introduce the basics of magnetohydrodynamics as a prelude to applying it to astrophysical situations such as dynamos, which is, as you would have guessed from the name, the phenomena by which magnetic fields are generated in astrophysical bodies. And we will also consider magnetized jets. These astrophysical jets that I alluded to a little earlier, they are often magnetized. They often entrain magnetic fields, and they're often confined by large-scale magnetic fields. So in order to understand this, you would have to understand magnetohydrodynamics first. So these are the astrophysical applications of magnetohydrodynamics, and so that pretty much brings us to the end of the overall outline of the course. And the books, the reference material that I'll be using for this course are Fluid Mechanics by Kundu and Cohen. I've simply said 4th edition here, but there might well be a later edition. I want to emphasize that there's an Indian edition available at a reasonable price. The other book I'll be using fairly extensively is The Physics of Fluids and Plasmas by Arnab Raichaudhuri. Also an Indian edition is available. I highly recommend this book. It talks about fluid dynamics as well as magnetohydrodynamics and even a little bit about plasma physics with a specific aim towards connecting to astrophysics. And of course, there's a classic book on fluid dynamics by Landau and Lifshitz. One can't go wrong with this kind of a book. So I will be, and in the course of what I'm doing, I will be borrowing some from Landau and Lifshitz also. Before I end this, I just want to emphasize that what I'll be talking about in this course is simply, you must simply regard it as a guide to reading the material in these books. Really, I mean, there's really no substitute for reading the book and for solving the problems in the book. What I'll be telling you in this course is merely, is merely snippets from these books, and so just merely a guide to reading these books. Concentrate on this, concentrate on that. This is a good way of understanding what this book is, what this particular chapter in the book is saying. Things like this. So the real repository are these books. And needless to say, there's plenty of other materials, there's plenty of other good books, and I will be putting up certain other reference material such as review papers and so on and so forth, and you will have access to that too.